Jim Bergmann with measureQuick. Wanted to spend a few minutes today and go over how to charge a system with measureQuick. And it's really important to understand, first of all, what refrigerant charge is and how we actually determine if the right amount is in the system. A lot of textbooks, believe it or not, don't show us this, and I think it's just some fundamental relationships we got to understand. So I got a little whiteboard drawing up here. I've got our compressor, our condenser, our metering device, and our evaporator. And I just want to talk a little bit about the state of the refrigerant in the system and what we're trying to achieve. So when we're talking about setting up the system, first of all, what we're trying to do is get a liquid seal in the condenser. So in the condenser, there's several things happening. We're de-superheating, we're saturating, which means we're turning to a liquid, and then we're subcooling that liquid down. And that subcooled liquid, subcooling means basically an easy way to understand it is above or below the boiling point, right? So if we're talking about water, water boils at 212 degrees. If we're 1 degree above the boiling point, in other words, 213 degrees, we're superheated. And if we're 1 degree below the boiling point at 211, well, we're subcooled. So superheat and subcooling just tell us above and below the boiling point. And the way we find the boiling point is, well, we measure the pressure on the gauge here. So let's say, we got some kind of pressure, maybe 300 pounds. We can convert that to a saturation temperature and determine our level of superheat or subcooling. Now the other piece of the equation here is we're trying to fully fill the evaporator coil without flooding it. So the evaporator coil is full of boiling liquid, and we're boiling that liquid off, we're changing state. We have the blower over here that's blowing air across the evaporator coil. It's blowing the air across, so we start, let's say, at 75 degree air. The refrigerant's absorbing heat and the air is coming out, let's say, 55 degrees, so maybe a 20-degree split across the evaporator, pretty typical. On the condenser side, we're taking the outdoor air, and so we'll have a fan over here. We have a condenser fan, and we're taking outdoor air that's maybe, let's say, 80 degrees. We're going across a 100-degree condenser, and we're cooling that air, cooling that coil down, and maybe the air comes out here, maybe about 97 degrees or so. So we're cooling that refrigerant down. Well, what we're trying to do is we're trying to get the correct amount of refrigerant, enough refrigerant in the bottom of the condenser to create a liquid seal, and we want a fully active evaporator coil on there. Now, depending on the type of metering device, and we'll just take this off for a minute, if this is a TXV, the job of the TXV is to maintain superheat. So if we go up here and we put a sensing bulb here, and then we have typically also we have what's called an external equalizer line. An external equalizer line, nothing flows through it. It's just a measure. We're measuring temperature here, so we're measuring the temperature of the line here, or sorry, pressure, scratch that, pressure here, and we're measuring temperature here. So when we have pressure and temperature, we can determine superheat. And the valve's basically got a spring setting that corresponds with whatever its factory setting is. Typically anywhere from about 6 to 10 degrees is where we're going to have that superheat setting on the valve. Now the cool thing with a TXV is its only job is to maintain superheat. It does not care what the suction pressure is. Its job is to maintain the superheat. The suction pressure is driven by the return air temperature. So as the return air temperature goes up, the suction pressure goes up. Also, a slight impact to humidity. Once the coil falls below the dew point temperature, moisture will condense in the coil, and energy from that moisture turning from a vapor back to a liquid will transfer into the refrigerant. But the primary driver is the temperature. The outdoor pressure is driven by the outdoor air temperature. So the temperature of the air, and also think about this for just a minute. We have this 75-degree air. If the blower speeds up or down, it's like turning up and down a burner on a stove, right? The flame temperature remains the same. So the air temperature is 75. The flame temperature is 2,000 degrees. But when we turn up the flame, we're turning up the quantity of heat. So the temperature, the heat intensity doesn't change, but the amount of heat changes, the volume of heat changes because we're turning up the burner. It's the same thing here with turning up the blower. So if we have low airflow, it's like having a low quantity of heat going across this coil, and we're going to have a low pressure on this. It's not the TXV causing the low pressure, it's the airflow that's causing the low pressure. The job of the TXV, again, is just to maintain superheat, which means it's maintaining the level of refrigerant in this coil. That's its job. Now, when you're adding refrigerant to a system, don't forget here, we're on the low side over here. This is our suction line. So this is our low side of our system. Over here is our high side of our system, right? We're going to add refrigerant over here. And it's going to take time. It's got to go through the compressor. It's got to go through the condenser. It's got to condense, desuperheat, saturate, subcool to a liquid down here. Liquid. And it's going to turn to a liquid. That liquid goes through the metering device and then slowly raises the level in the evaporator coil. Now, it only slowly raises if there's not enough refrigerant in the evaporator coil. If the superheat's fine, then what's going to happen is the TXV is going to shut down and we're going to back up liquid in the condenser. So once the TXV has enough refrigerant, or once the system has enough refrigerant for the TXV to maintain constant superheat, the superheat will remain the same. So we'll probably run, like you said, or somewhere around that 6 to 10 degrees of superheat. 6 to 10 degrees of superheat, but the subcooling will start to increase because we'll start stacking up liquid in that condenser. So we'll take our subcooling, let's say from 7 up to 10, right? So the subcooling will increase as we add refrigerant. Now, if we change the metering device to a fixed type metering device, in other words, we get rid of our TXV, we no longer have temperature, we no longer have pressure here, and we have a fixed metering device. Well, that's just simply a hole, fix MD. It's just simply an orifice through there. And this becomes a little bit more of a balancing act. So we add refrigerant over here, it increases the pressure on the condenser, it pushes down, right, because we're pushing on the top of that liquid, which means the liquid level is going to go down, evaporator level is going to go up, superheat's going to go down. So and once we get that liquid seal in there and we add refrigerant, we're effectively reducing the amount of condensing space, right? And this metering device does not maintain a constant superheat. The superheat is calculated by the return air wet bulb. So in here we're looking at temperature degrees plus RH. So this is a wet bulb temperature, right? We want to get entering wet bulb and we get outdoor air temperature. Those are the two drivers for the target superheat for this. So we ultimately, before we charge a system, there's a couple things we need to know. We need to know that A, the evaporator coil is clean, the condenser coil is clean, the filter is clean, right? We need to know that our airflow is in the correct range. It's very critical that we know our airflow is in the correct range before we start charging the system. And then we need to know our metering device type, so we know whether we calculate our superheat or subcooling, because again, a fixed orifice is charged by superheat, a TXV is charged by subcooling, so two different methods of charging. And once we know those variables, then we can let measureQuick do the rest of the magic and help you with the charging process. So let's walk over to another system here we got running, and I'll walk you through that charging process. All right, so before we get into charging a system, it's really important that we do a couple of things. And I'm going to have Valerie come over here and just get in so we can see some of the stuff. But one of the things we want to do is we want to take a close look at our blower wheel. So I'm going to turn on a flashlight here just so we can see inside here. And come over here, let's just take a peek at the blower wheel. You can see that the blower wheel in here is very, very clean, right? It's got just a tiny bit of dust on it. On this system's been up and running in our labs for quite a few years right now. And the blower wheel is very, very clean on here. So we want to make sure that we have a clean blower wheel, because we're going to do a quick test of airflow and we're going to use static pressure to do that. So if the blower's not clean, it's not going to agree with the static pressure chart. The next thing I want to do is come down here and I'm going to check my filter and I'm going to check my evaporator coil again before we start doing testing on this. So my filter here, relatively clean. That looks like in really good condition. I'm going to turn on my camera here and I'm going to sneak up under here and I'm going to just take a photo. All right, so we got a photo and you can see the evaporator coil is pretty clean here. It's what we're seeing, just a little bit of moisture on the evaporator coil from it running earlier on here, but a very clean evaporator coil. So go ahead and slide the filter back in place and we'll make sure the airflow is correct here. So airflow going up, filter going in, slide that back in place. So we've got a clean filter, we've got a clean blower, and we'll just go ahead and put the screws back in. And I'm going to turn the system to cool, and we'll let the system start up and start running. Now also we obviously want to do a quick visual inspection of our condenser coil. Which you can see, this condenser coil is a little bit dirty here. So we should probably clean that before we charge the system, right? And it's very hard to see this unless you get in close and you actually look at for dirt on the coil, but this will actually impact the operation of the equipment. So we'd want to clean this off before we actually do the charging. All right, so we just got done cleaning our coil with a Subcoat Portablaster. It's a really slick tool. If you haven't seen one, it's actually worth looking into. It's great for inside like this where we can just use a 5-gallon bucket full of water and clean our system out. We got this thing drying up, and so while it's drying, we're going to go over here and we're going to measure airflow real quick with a manometer to make sure we're in the right range. Now, it's really important that you get some kind of verification of airflow. Now, static pressure measurement is an estimation of airflow. It's not a measurement like we would get with TrueFlow Grid or like the estimated airflow calculation, but it will tell us we're in the ballpark. So you can see right here that I have this set up. I have a manometer in the supply, and then I have also I have a static pressure tip in the supply, and then I have a static pressure tip down in the return. And a static pressure tip, let me just show you one of these, is different from a pitot tube. Static pressure tips don't have a hole in the end. It's solid on the end, and it's got these small holes on the side, on both sides of it, and it's just measuring the bursting pressure or the pressure inside the ductwork. So I'm going to have one in the supply, one in the return. There's an arrow on these tips that shows you direction of flow, so it can actually go this way or this way. It just needs to go in the direction of flow. So I'm going to have this set up like this. I've got one down here, and I'm going to have Val come down here and take a quick shot here so you can see this. The probe has got to go after the filter. So I'm getting out a flashlight here just so you can see inside here for a second. And if we go inside here and you just take a peek, you can actually see the static pressure tip, and it's after the filter here. So we don't want to include the filter in the static pressure measurement because these air handlers are rated without a filter. So if we go to the directions here, a couple of things. Okay, so airflow data is indicated at 230 volt without the filter in place. Okay, so that's how we know that this is rated without the filter, and it's charged for informational purposes only, and it must not exceed the value. And so let's take a look here. So we are at 0.25, 0.26 inches of static. So we're in between this range, so we have to do what's called interpolation. So we're between 620 and 595, so we're somewhere around 600 CFM airflow. This is a 1.5 ton condensing unit, so we want to set the airflow for the condenser. The air handler here is a 025, which means it's a 2-ton air handler. Goodman does not make a 1.5 ton air handler. They pair their 1.5 ton condenser with a 2-ton air handler, and so we have to run it on low speed in order to get the airflow correct. If you look at this chart again here, you can see low is in the 600 CFM range. So this would be for like a 1.5 tons. Medium is about a 2-ton, and then we get up to 1.5 tons here on the high speed on this system, or maybe closer to 450 CFM per ton. So now that we have all those things done here, we got airflow correct, we're in the ballpark anyway. Now we're in a position that we can actually check the charge on the system. All right, so now that we've got everything all set up, we got the condenser coil cleaned, we've checked the filter, we've made sure our static pressure's in range, our coil's clean, our blower's clean. Now we're okay to check charge. It's very important that you don't skip that step. A lot of people want to go immediately engage up on a system before they make sure everything is clean and the airflow is correct, and that's where you really make the biggest mistakes in our industry. So those preliminary steps are very, very critical to making sure that the system's actually going to operate correctly. Now, this system here, if we look at the air handler on here, this is where the metering device is at, and you can see here that this is a piston. So if this was TXV, it would actually have the TXV would be right here, but we also put the label on for the piston. So this is an 051 piston, or 51 piston size on here. And that 51 piston just matches up with this condenser. So we're going to set the airflow and the metering device for the condenser. Now, we know this is a fixed orifice metering device, so the superheat is going to be calculated. There's a target superheat that's going to be calculated by the measureQuick application. So let's go through and let's take a look at this profile here and get this set up. So we have this set for refrigerant 410A, and I'm going to go in here and just go into the profile here. We have a split system, rotary compressor. 2021, ton and a half, 410A. It's a standard efficiency, so we're doing SEER 13 to 16 with a piston, which means the superheat's auto-calculated. Minimum subcooling we have at 3 degrees. Rated external static pressure is 0.50. And again, we get that if we come down here on this label here. Test external static pressure. Test external static is 1/2 inch of water column. That doesn't mean you can't go above that or below that, but that's what the system was rated at or tested at, was 1/2 inch external static pressure. So now I'm going to hit continue. Now, again, this is really important. We have this set up as a piston metering device because that's how our superheat's going to be calculated. And I'm going to go ahead and tap on the outdoor reading, the sun button. It's going to show us our outdoor measurements. Now you can see right here our superheat is within range. Okay, so it's 17.7 degrees is the actual measured superheat. But if I tap on this target, and it'll show me my current value 17.7, my calculated target is 20.0. Okay, and so that range is allowable is 15 to 25 degrees because it's plus or minus 5 degrees of superheat. If I click on this Get Schooled button, it'll actually walk me out to an article on this, and I'm going to scroll down a little bit. So you see the superheat charging chart here. So we're at about 80 degrees here and about 67 wet bulb, which is about that 20 degrees target superheat. So that chart that's in this app is actually built into measureQuick, and we're doing those calculations for you automatically. As the outdoor temperature changes or the return air wet bulb changes, like the system settling down, those targets are going to change as we go. All right. So let's look at another thing here that's just interesting here. I'm going to go into performance for a second, and I'm going to tap on my performance and look at my airflow. Now we said that measureQuick was moving around 600, or the blower chart said we're moving around between 600 CFM, right around 600, a little less than 600 CFM. measureQuick is actually showing us 551 standard CFM. And you also see below that, it's the actual airflow is 589 actual CFM. This is a PSC blower, and a PSC blower moves a constant volume of air independent of the air density. We're talking about standard air, we're talking about a weight or mass of air. And so we're moving, in this case, 552 standard CFM, which means that a standard CFM is 0.075 pounds per cubic inch. But in this case here at the shop, we're about 80 degrees and we're high humidity, so our return air density is 0.070. So we would not want to adjust the blower on this, even though the standard CFM is low, because when the temperature and the humidity drops, the air density will go up and we'll be moving that 600 CFM that are required for this 1.5 ton system. So the airflow, when you're on a PSC, always pay close attention to the actual CFM, not the standard CFM. On an ECM motor, we almost always look at the standard CFM airflow. All right, so we got all those things right. Superheat's in range, charge is correct, so we don't have to adjust this, but I'm gonna pause the video for a second. I'm gonna show you a couple more things. Obviously the refrigerant charge on this is fine, but I'm gonna actually show you how we'd add refrigerant. And so right now what I've got is a hose that's purged, but obviously there is air in the end of this hose right now. So what I wanna show you though is a lot of people think when you open a hose up like this and purge it, that you're not getting all the air out, and as soon as I shut this off, it's going to allow air to enter back in the hose. If you watch this with a thermal imager here, so I've got this set up so you can see the refrigerant coming out of the hose. I'm gonna slowly crack this open, and you'll see the refrigerant vapor come out of the hose. So you can actually see it coming out of the hose. As soon as I shut that off there, you'll see that nothing's falling out of the hose. And it's just like you put your finger over the end of a straw, like if you were to put it in a can of Pepsi and put your finger over the end, nothing can flow out and nothing can flow in. So you can see when I shut this off here, because the refrigerant's blocked on the one end, that the whole hose is now primed with refrigerant, and we can go ahead and attach this to our fitting and not get any air in the system. All right, so let's go ahead and we'll hook up our hose here. And what's nice with these JB probes is that they actually have, if you turn them to their side here, they've got a charging port on the back of them here. And because I can actually see the display on my app there, I don't have to see the display in the probe. So I'm gonna go ahead and pull this back. I'm gonna just fit it on loose, give it another purge here just to purge out any air and snug this up. So now I've got the refrigerant hose attached and I've got the valve closed for my refrigerant. If I was going to add refrigerant, you always have to add blends as a liquid. So I turn this drum upside down here, and then we can add a small amount here just to see what's going to happen here. So you can see we've got 18.3 degrees to superheat, and I'll add a little bit of refrigerant into my low side, and I'm just adding just a hair in there. You can see right away my suction pressure goes up and my superheat's starting to come back down here. So we'll let this settle out for just a minute, and let's just watch our trend here. We'll go to our trends and we'll actually just reset this, restart trends. And you can see that's high and low pressure. So let's go back one to superheat and subcooling. All right, so you can now see our superheat, which is the red line, is in range, but it's starting to creep up a little bit. And our subcooling is coming down a little bit. And so we'll let this just settle out for just a minute because we monkeyed the charge. What we should see is our superheat going down and our subcooling coming up. And so we'll make sure that's what's going to happen here. Let me all right, so we'll add another small amount of refrigerant here. When we added that refrigerant in, what's going to happen is you're going to get a pretty massive change at first, but you can see now that when we added that in there, now it's dropped from where it's at, and it'll continue to drop. We'll let it settle out for just a minute, and we'll see if it continues to drop off. So here we're at about 18.3 degrees of superheat, and now we're down to about 17.6. And again, our target range is 20 degrees. So this is the center of our target, plus or minus the 5 degrees. So you can see adding the refrigerant in lowers the superheat. And you can see our subcooling was started out about 10, and we're up to about 10.9 right now. So it's just a small amount of refrigerant we added, but you can see how that's impacting the refrigerant charge. So that's all there is to it. We make sure that, again, we make sure that we check the filter, make sure it's clean, check the evaporator coil, it's clean, check the blower, make sure it's clean, check the condenser coil, make sure it's clean. Make sure everything's clean before we adjust charge. Check our airflow, at minimum by static pressure, just by getting a quick static pressure reading to make sure we're in the right range. And then we can start to charge the system. And again, we identify the metering device to make sure that we either are charging by superheat or subcooling. And then again, if we're in measureQuick and we want to know what our targets are, we just go to the superheat and we tap on the target. It'll tell us what our current value is, in this case 17.3, and our calculated target's 20.4. So that will adjust in real time as the load changes. Again, because we're on a fixed metering device, but that's all there is to it. It's very simple. It's just a matter of making sure that we do the basics before we get into monkeying with the refrigerant charge. This is Jim with measureQuick. Thanks a lot for watching.